All right, so welcome to chapter 16, where we are going to discuss air quality and air quality issues. And so, with this chapter, we are going to talk about the atmosphere. We're going to talk about the structure of the atmosphere and the basic kind of gases and molecules that make up the atmosphere. We're going to look at pollution, categories of air pollutants. We'll talk about photochemical smog. We'll talk about acid deposition. We'll look at ozone depletion, how we can control air pollution, look at air pollution and how we can kind of move forward with developing countries and the developing world. We'll talk about indoor air pollution, and then we'll finish up with just kind of brief discussion of noise pollution. Atmosphere. So the atmosphere is composed of approximately 78% nitrogen, 20% oxygen, and about 1% other gases. So things like carbon dioxide, methane, water vapor, etc. Most of the atmosphere, so most of those gases are held close to the Earth. And that's the gravitational force that's kind of pulling those gases down and holding them close to the Earth's surface. And because gravity is holding those gases close to the Earth's surface, the atmosphere gets less dense the farther you get away from the Earth's crust. The gravity gets less. And the atmosphere can actually be separated into kind of several different layers, depending on kind of some characteristics of those layers. Is the lower layer of the atmosphere. So this extends from the Earth's surface to about 10 kilometers above the Earth. Above the troposphere, you have the stratosphere. And so that's between 10 and 50 kilometers. And then the ozone layer is basically within the 15 to 30 kilometer band. So that area in kind of the middle of the stratosphere. So that's where the ozone layer will kind of be. Then above the stratosphere, you have the mesosphere, which is 50 to 80 kilometers. And then the thermosphere extends from 80 to about 300 kilometers above the Earth's surface. And with the different levels of the atmosphere, you have kind of a temperature gradient that occurs from the Earth's surface into the upper air portion or atmosphere. And the way air moves into the atmosphere is that at the Earth's surface, it becomes heated due to the incoming solar radiation. And as it heats, it expands. And because it expands, it becomes less dense. And as it expands and becomes less dense, then it rises up in the atmosphere. When that air cools, it becomes more dense and then flows back down towards the Earth. And so you kind of have this cyclical effect with the atmosphere, in that gases will warm, they will rise up, gases will cool, and they will flow back down. And this air is also being replaced in the upper area of the atmosphere and at the Earth's surface. And so it's circulating vertically. And then also, so if you combine that vertical circulation with the fact that the Earth is moving and spinning around an axis, it causes the air to move horizontally. So part of the Coriolis effect. Now, you combine this vertical movement with a horizontal movement as the Earth is spinning, and this combination of air patterns, these combination of air movements, is what creates the wind along the Earth's surface and what leads to the overall general global weather patterns that we see around the world. Now, there are these micro effects, so like local topography, local kind of environmental conditions or geological conditions that lead to small variations within that regional climate. But typically that regional climate kind of has this generality associated with it, kind of where the air is rising and where the air is descending. Now this figure shows the different atmosphere. So the troposphere, like we mentioned, is up to 10 kilometers, which is almost as high as Mount Everest. It's usually where your jets will fly, so around 30,000 feet. The ozone layer is shown here in blue, is located in the stratosphere, which is above the troposphere. Then you have your mesosphere and your thermosphere. Now here's an image of the global wind patterns that occur. And remember, these wind patterns occur because of the vertical and horizontal circulation and the rotation of the globe. So for example, we have different weather sails or different sail cycles, atmospheric cycles, or atmospheric sails that exist. And so, for example, there's a sail between the equator and 30 degrees north and south. And so at the equator, solar radiation is coming in and it's heating that air. And so that hot air is rising. And as it rises, it cools and it falls as rain. So the moisture in the air falls as rain. So that's why the equator is a rainy place. That's why it has those tropical areas. And then as that air rises, it then moves horizontally across the upper atmosphere. And then as it's moving horizontally, it's cooling down. And as it's cooling down, it starts to get more dense and it starts to sink. And so at 30 degrees north and south, you have cold, dry air that's sinking down to the surface of the earth. And so at 30 degrees north and south, you have deserts because you have that cool, dry air that's coming down. So there's really no clouds because there's no moisture in the air, no rising moisture to condense and to form clouds. And so that's why we have these typical patterns of weather, say at the tropics and 30 degrees north and south. And then once that air reaches the Earth's surface, it then moves towards the equator to replace the rising air at the equator. And so you have this cyclical or this sail that exists between the equator and 30 degrees north and south. And then you also have two other sails. So it's the Hadley sail, the Ferrel sail, and then the polar sail. And those exist both north and south of the equator. And now another interesting aspect is that the Earth, like we mentioned, spins. And so if you have a vector of wind so if you have wind blowing in the southern direction, and based off of the way the Earth spins, that wind will be deflected to the right in the northern hemisphere and the left in the southern hemisphere. So this is kind of the generality of the Coriolis effect. And so because that wind is moving southward to replace the air mass that's moved upwards at the equator, cause it to bend, and so that's why the winds move from or blow from north from northeast to southeast in the northern hemisphere, and from northeast to southwest, and then from southeast to northwest in the southern hemisphere. And so basically, if you follow the vector, right, winds going to the equator to replace, bends to the left in the lower southern hemisphere, the Coriolis effect is causing that bending wind pattern. If the Coriolis effect, the Earth wasn't spinning, Coriolis effect didn't exist, then these red arrows would be vertical arrows, right, that did not have a bend to it. Okay, so that Coriolis effect is causing that bending pattern. Okay, so next looking at the pollution of the atmosphere. So pollution basically is any addition of matter or energy that is harmful to the environment or for humans or for any other organisms that live in the environment. It causes negative impacts to those organisms or to the environment they live in. Human actions are the major cause of pollution. And so we have a direct way to prevent pollution. So we can prevent it by just not doing the activities that cause that pollution. However, we rely on a lot of those activities to survive and to undergo our day-to-day lives and to get resources we need, etc. And so it's really hard to just stop those pollution sources. So we have to figure out ways to kind of keep doing the things that we need to do to survive, but to also try to mitigate pollution in any way we can. And so a lot of the primary emissions come from automobiles, chemical odors, smoke from factories, smoke. And so like any particulate matter that goes into the atmosphere is generally considered some type of pollution. Air pollution is actually directly related to the number of people living in an area. And so in urbanized and industrial areas where you have a densely concentration or a dense concentration of people, population's dense, then you have large quantity of fossil fuels being burnt, a lot of people driving, and so your quantities to the atmosphere and put into the environment that is a direct result. In urban areas, the pollution can't be diluted really before it reaches another city. So for example, pollution from Chicago is further polluted when it reaches Gary, Indiana, which is nearby. It's also supplemented by waste from Detroit and Cleveland, and then finally we'll move over southeastern Canada to New England and then into the ocean. And so you have this problem of, again, just because you pollute in one city doesn't mean that it stays there. Remember, nature doesn't follow our boundaries. And so atmospheric pollution is, and even, water pollution and all other sources of pollution, as a matter of fact, don't follow our boundaries. And pollution is just not an aesthetic problem. So it's not that the atmosphere looks hazy and looks nasty and looks dirty, but it actually causes health problems, which we're all probably aware of. And those health problems can be fatal if they become severe enough. A lot of the megacities of the developing world have extremely poor air quality. Again, this is from all of the activities that we do on a regular basis. And as the air pollution increases, health is going to go down in those cities. And so the death rate will increase, and then the general health of the population will go down. So here's some images that are really showing kind of the air pollution and the population centers. You can see the darker areas are where your population densities are the highest. And then you can kind of look at the areas where the pollution is the largest. So the darker areas is really large pollution. And unfortunately, in the state of California, a lot of the bigger cities in California are some of the most polluted cities in the United States and in the world in some cases, depending on which city you look at. So next, we're going to kind of go into the different categories of air pollutants that exist. So there are 5 big types of materials that are released into the atmosphere. And these can pose a health risk when they're released in sufficient quantities. And these materials are what we refer to as primary air pollutants. So these big 5 are carbon monoxide, VOCs, or what's also known as hydrocarbons. Those are volatile organic compounds. Particulate matter, so particulate matter that comes, say, for example, from burning wood or burning a wood stove or a fireplace. Sulfur dioxide, and then various oxides of nitrogen. And so we're going to talk about each of these kind of individually over the course of this chapter. Another category of air pollutants are secondary air pollutants. And these form under the reaction of primary pollutants combining with water or sunlight, and this leads to the production of ozone. So ozone, while good in the upper portion of the atmosphere, because it helps blocks incoming solar radiation, it is a form of pollutant when it's kind of in the wrong place in the atmosphere, or in concentrations that don't need to be kind of around humans. There are criteria air pollutants that there has actually been standards set on how much of those air pollutants need to exist. And if you go over those standards, then there are big issues that can come from that. So these criteria air pollutants are things like ozone, nitrogen dioxide, sulfur dioxide, particulate matter, carbon monoxide, and also lead. So first, looking at carbon monoxide. So carbon monoxide is produced when organic materials are burned with insufficient oxygen. One of the biggest sources of carbon monoxide is exhaust from automobiles. 50% of the vehicles, 50% of carbon monoxide comes specifically from vehicles that are driven on highways. You also have other machinery and vehicles that are not used on roads that produce carbon monoxide, so like ATVs, off-road vehicles, tractors, etc. And then there are other percentage of carbon monoxides come from burning, so burning yard waste, burning wood for fuel, and then also burning fossil fuels in power plants. The carbon monoxide is bad because it binds to the hemoglobin in the blood and makes it less able to carry oxygen. So if the carbon monoxide is bound to the hemoglobin, then oxygen can't bind to it. So therefore it can't carry oxygen through the body. Carbon monoxide is really dangerous in enclosed spaces. And if you have a couple hours of exposure, you could eventually die from carbon monoxide poisoning. And it is fairly common for children or for animals to be in cars or vehicles, say in a garage that's left on, and they can die from carbon monoxide trapped in the garage. Cigarette smoking is an important source in terms of carbon dioxide affecting humans, because the carbon dioxide is inhaled directly. So it comes directly from the cigarette smoke into the person's lungs and into the person's body. If we look at carbon monoxide concentration in the world, it's decreased by about 77% between 1970 and 2015 in the US. And so again, here's just a picture of, congested roadway transportation, seen highways like this in San Francisco or LA, depending on what area you're from or you've been to. So just a lot of pollution that comes from those automobiles. Next is particulate matter. Particulate matter consists of just little pieces of material and liquid droplets that go up into the atmosphere. Particulate matter is defined as any material that's less than 10 microns. And we can actually classify particulate matter into two different categories. So we can do particulate matter 10 microns or less, and particulate matter that's 2.5 microns or less. So the particulate matter that is the larger forms, so like PM10, are the primary pollutants. If it's PM 2.5, then those are classified as secondary pollutants. And then the particulate matter can actually accumulate in the lungs and interfere and decrease our ability for respiration to occur. And so inhaling particulate matter can actually be really bad for our respiratory process. Particulate matter, so PM10, has decreased on average by about 39% since 1990 and 2015. The US has been trying to get a particulate matter 2.5 micron standards for a shorter period of time. And between 15 years, so 2000 and 2015, we've had about a 37% decrease in particulate matter. Now, most communities typically meet the standards for particulate matter 10 microns or less, but a lot still exceed the standards for particulate matter of 2.5 or less, so that's smaller particulate matter. And so we're still trying to get a good handle on regulating and controlling how much particulate matter makes it into the atmosphere. The next pollutant we're going to look at is sulfur dioxide, so SO2. This is basically a compound of sulfur and oxygen, and it's released as a product when you burn fossil fuels. 70% of the sulfur dioxide released today is from coal burning power plants, so burning that fossil fuel to make energy. Sulfur dioxide concentrations, so from 1990 to 2015, have decreased by approximately 81%. Most communities meet sulfur dioxide standards set by the Environmental Protection Agency, which is pretty good. Nitrogen dioxide or other forms of nitrogen oxides, so NOx, and the X could be, NO or NO2 or any other form. These are also formed as a byproduct of fossil fuels. And so the nitrogen and oxygen molecules in the air basically combine with one another when you have high temperatures, and they form nitrogen monoxide, so NO, and nitrogen dioxide, or NO2. The fossil fuels, say like from internal combustion engines, really produce these nitrogen oxides, so automobiles, off-road vehicles, and then also generators that produce electricity produce a large portion of the nitrogen dioxide that makes it into the atmosphere. About 75% of the nitrogen oxide that is produced by automobile engines is converted back into atmospheric nitrogen, so N2 and O2, by a catalytic converter. So this catalytic converter is a machinery part that actually exists in the car. But as the cars become older, as they become driven and they get more miles, the change in the catalytic converter, or the efficiency can go down, it doesn't work properly. But then also because there's just a large amount of numbers of cars on the highway, and their cars drive a ton of miles, it basically offsets the gains that catalytic converters contribute to reducing, the emissions of nitrogen oxides. And so a lot of communities meet the EPA standards for nitrogen oxides, but they remain a problem because they can allow for photochemical smog to develop. And we'll actually talk about photochemical smog and talk about how it develops. But basically, you have primary pollutants that are in the atmosphere. So things like sulfur dioxide, nitrogen dioxide, carbon monoxide, and you combine those things with water and heat from solar radiation, and that forms photochemical smog. And so although we are below the standard levels that we deem necessary for nitrogen dioxide in the environment, there's still nitrogen dioxide in the atmosphere that allows for the production of photochemical smog. Now, one of the final kind of big primary pollutants is lead. And so lead can enter the body through the respiratory system, or by consuming lead that is on the surfaces of something that you eat. It accumulates in the body, and it can cause kidney damage. It can affect the brain and cause mental retardation, can cause brain or mental issues. And one of the kind of big sources of lead was leaded gasoline, but that leaded gasoline has now begun to be, or has been, phased out. And so lead is really no longer used as an additive to gasoline, and almost all gasoline produced now is known as unleaded. And so the US had lead emissions to peak at about 258,000 tons per year in 2014. They were, or I'm sorry, so they peaked at about 258,000 tons per year. In 2014, they were significantly lower by about to about 730 tons per year. So we're looking at like a 99.7% in or decrease in the amount of lead that's being released into the atmosphere. Now so I lied to you. We are going to talk about another primary pollutant, and we mentioned these whenever we listed those, and these are the volatile organic compounds, or what we know as VOCs or hydrocarbons. So these volatile organic compounds, they evaporate and then they become pollutants in the air once they evaporate into the atmosphere. They're called hydrocarbons because they're primarily composed of carbon and hydrogen. Now, sources of the VOCs come from car engines, combustion engines, right? They emit almost all of the primary pollutants, other solvents we use, and then other industry activities. And like we mentioned earlier, primary pollutants contribute to the formation of smog, and VOC is one of those primary pollutants that lead to the production of smog. So here's some examples of products that you could use or may use that has volatile organic compounds that can lead to, the conversion of these compounds, adding to VOCs being put into the atmosphere. Okay, so there are lots of dangerous chemical compounds that can affect human health and negatively affect the environment. And, some of those are released on purpose, which is sad to say, and then others are released accidentally. Regardless, they get put into the environment in which humans and the environments interact with, and organisms that live in those environments interact with. Those compounds are what we refer to as hazardous air pollutants, or HAPs. These are things like pesticides, the benzene that exists in gasoline, and then other products like cleaners, and then some glues that we use. Most of the air toxics are released in that manufacturing process to make those products. So for example, perchloroethylene is released whenever you dry clean your clothes. Petroleum, right, is one of the primary sources of hazardous air pollutants. And so chemical and petroleum industries release HAPs as byproducts. And the exposure of these HAPs are not good in any sense that they're released into the environment. But for people that work in those industries that release the HAPs, they have this kind of constant exposure where that exposure can become much more serious when they're on the job. And so they can be much more harmful for people that are working in that industry. And so we mentioned that photochemical smog will form as a result of some interactions from primary pollutants, water, and solar radiation. Well, photochemical smog is a pollutant that is kind of involved in the production of secondary air pollutants. So these secondary air pollutants are basically pollutants that are created from pre-existing pollutants. And so photochemical smog really is just a mixture of pollutants. And so it basically forms when you have nitrogen dioxide, so NO2, your VOCs interacting with other primary pollutants with sunlight present. And some of the or some of the worst components of the photochemical smog are ozone and peroxyacetyl nitrates, which are also known as PAN. And so ozone is 3 oxygen molecules bound to one another. And like I mentioned, ozone in the upper atmosphere is really helpful. It screens out ultraviolet radiation. It helps prevent that radiation, that harmful radiation, from reaching the Earth's surface and say harming our skin, and not, you know, giving or not allowing us to come in contact with all of that radiation. And so, however, though, ground level ozone, so ozone that's not in that upper atmosphere, so like in the stratosphere, is a serious pollutant, and can be really harmful to humans and other organisms. The way smog forms is that you have to have all of these ingredients that we've mentioned and talked about already. So the nitrogen oxides, the VOCs, and then you combine them with sunlight and higher temperatures, and that sunlight and temperature facilitates chemical reactions between those primary pollutants. And so in most urban areas, the nitrogen monoxide, the nitrogen dioxide, and the VOCs are present as byproducts, those pollutants that come off of, say, burning fossil fuels or running vehicles or making products. And then the sunlight and the warm temperatures are just a natural component of the climate and the atmosphere and, you know, the environment. And so you get smog to form. And so here we see the presence of, where is my pointer? Hold on, let me get it. Okay, so you can see the different pollutants that are present. And what's interesting is you have pollutants that are made by like automobiles and, you know, industries that run during the day. And you can see that those pollutants kind of drop at night, but then in the morning when everybody starts traveling to work and starts, you know, running their machines, the pollutants peak. And then after about lunchtime, they start to level off into the evening. And this is because when they, you know, at night, there's no sunlight to key this reaction of photochemical smog. During the morning, all of the new primary pollutants are put into the atmosphere, and then you have the sunlight from the daytime. And so the pollutants peak, but they start dropping down because they are getting used up in that photochemical smog production. Then in the evening and at night, everybody goes home and they stop driving, not as much traffic, and so those amount of pollutants go down. And then the next morning when activity starts again, they'll go back up, smog will be produced, cause them to go down, everybody goes home, and they tend to level off. And so that's kind of how that photochemical smog production basically takes place. And now, like we mentioned, if you live in an area where it's warm and it has lots of sunlight, you're going to develop more smog because you have more of those factors present that are keying in and causing that chemical reaction to happen. And so smog is a really big problem in summer, where you have high temperatures and you have longer days because there's much more sunlight available throughout the day to allow that chemical reaction to happen. Also, cities that are near mountains or valleys have trouble with smog because the pollutants actually become trapped in those valleys by thermal inversions. And so thermal inversions are basically where you have air layers kind of trapped underneath one another. And so we know that warm air is less dense than cold air, and so it rises. But a thermal inversion basically is where you have warm air being trapped between two layers of cold air, and it basically acts like a cap. So the warm air can't diffuse up out of the valley because the cold air layer, say on top of the valley, prevents that warm air from rising. And so you get smog accumulation because there's no mixing of that atmosphere when you have a thermal inversion. So between the time of 1990 and 2050, ozone levels fell by about 38%. But there's still a big problem, especially in Southern California and in the northeastern area of the US. Ozone, right, is produced by your VOCs and your NOxs. So it's necessary to reduce the concentration of these two primary pollutants in order to reduce the concentration of ozone. And so again, if you look, that concentration of ozone, this line here, it follows those patterns, right? So none in the morning really, because all of the primary pollutants have been used up, increases right after the peak in those because they're being used up to make the smog, and the ozone goes down, right? So you have that daily cycle. Here's an image kind of showing this thermal inversion layer. So basically, when you don't have a thermal inversion, you have this situation on the top. Air mixing, warm air going up, cold air coming down, your pollutants are dispersed. However, when you have a thermal inversion, you have cold, dense air flowing down the mountains into the valley. The dense air pushes the warm air up, and then that cool air isn't able to mix with that warm air. And so you have this inversion layer allowing those pollutants to basically stay in location. And so you have this cool air keeping that warm air underneath, not allowing it to go up past this cool air layer into the warm air above. And so that thermal inversion layer, again, is basically acting like a cap in that valley. So next, we're going to look at acid deposition. So acid deposition is where you have an accumulation of acid-forming particles on the surface. So basically, when you have dry particles deposited, the acid doesn't actually form. It only forms when it mixes with water. And so the sources that have, or I guess the sources of the acid-forming particles are referred to as acid rain. And these acids can affect things like, or they can come from natural sources. So vegetation, volcanoes, lightning, but they also can come from human activities. Like we've talked about earlier, burning things, coal, fossil fuels, oil, and running automobiles. And acid rain is a problem that's, a global problem. It's not just in one location. And acid rain will break down structures and materials like rocky structures, concrete structures, and you really can see the weathering on this tombstone where you can barely read the inscriptions because of the weathering and the acid rain that's affected it. And what we end up seeing with the acid rain is that as the lakes become more acidic, you get a loss of different organisms. When you lose those organisms, the food webs become less complicated and more linear. And then you have organisms not getting enough resources. They fail to reproduce. Others will die. Populations go down. And so the acid rain contributing to a change in pH can really be detrimental to a lot of aquatic and terrestrial ecosystems. At a pH of 5.5, your desirable fish species are basically prevented from existing in that aquatic system. When you get to a pH of 5, you're only going to have a few fish around. And then lakes with a pH of 4.5 are pretty sterile. No, or is very little organisms or very little life is going to be found in those acidic lakes. And when you have this acid deposition, when you have this acid rain, the effects that it has on an ecosystem is actually dependent upon the geology of the ecosystem and the surrounding area. And so, for example, Eastern Canada and the Northeast of the US is susceptible to acid rain because of their proximity to acid-forming pollution sources, and then also the type of rock, the type of bedrock, the parent material in those areas are really susceptible to being broken down and eroded as rain falls from the atmosphere. And so the way acid rain forms is you have those air pollutants like sulfur dioxide, nitrogen oxides. These are your acid particles. They mix with the rain, the water, and that acid rain falls out either as snow or fog. And then that can lead to the formation of, say, your sulfuric acid, your nitric acid, again, falling out and running into lake ecosystems, running onto crops, killing trees, affecting river ecosystems, and also affecting structures that we build. Okay, and so we've mentioned ozone as a pollutant whenever it's at the ground layer. And I've also mentioned that the ozone is good whenever it's in the stratosphere, so in the upper atmosphere. In 1985, the scientific community discovered that the ozone layer had basically thinned significantly over Antarctica. And that this thinning occurred during the spring of the southern hemisphere. And this thinning was known as the ozone hole. So you probably have heard about the hole in the ozone layer. Now, the ozone, like I mentioned, that layer shields the Earth from harmful ultraviolet radiation. Well, the reason that the ozone was thinning is because there were chlorofluorocarbons, so CFCs is what they're known as, that were released into the atmosphere through the use of products that contain these chlorofluorocarbons. And it takes a long time for those chlorofluorocarbons to get into the upper atmosphere, so anywhere from 10 to 20 years after they were released. But they can remain in the atmosphere for up to 20 years and continually react with the ozone layer. So once this was found out, once it was discovered, scientists basically said we need to do something or we're going to destroy the ozone layer and we're going to have vast consequences because there's a lot of solar radiation that's going to come in and affect global organisms and environments. And so in 1987, a lot of industrialized countries agreed to basically stop the production of chlorofluorocarbons and to, well, not really stop, but to, so they froze it and then they wanted to reduce the production by 50% by the year 2000. And this document, this agreement, is what's known as the Montreal Protocol. And a year after this protocol was adopted, the emissions of the CFCs dropped 87% relative to their peak amounts in 1988, or I should say not a year after, but a year after the protocol, Congress ratified it the next year. And then because of that ratification, because of putting action into reducing CFCs, you get a substantial drop in CFC emissions of 87% compared to their peak numbers from the year 1988. And so this shows that we can actually control pollutants and do something meaningful in terms of, protecting the environment and regulating our emissions. And so all of the pollutants that we've kind of discussed are all a factor of human activity. Now, carbon monoxide and sulfur dioxide, so those things can be released into the atmosphere through things like volcanic eruptions or geological activity, so those sorts of natural occurrences. But it's nowhere near the amounts that we're putting in the atmosphere ourselves. And so what this basically means is that the pollution can be curbed and it can be controlled based on our actions. And so the United States implemented requirements known as the Clean Air Act that has been their primary focus of controlling and affecting air pollution. The Clean Air Act is actually not one piece of legislation, but it's multiple pieces of legislation kind of working together. And the original act was ratified in 1970, amended in 77, and then amended again in 1990. The original act gives the Environmental Protection Agency multiple responsibilities of regulating pollution and air pollution in the atmosphere. And so some of those responsibilities are things like establishing air quality standards. So telling us what is the standard that we need to fall below in order to keep a somewhat healthy atmosphere and environment. They also have to develop strategies so that we can meet these standards. And then they need to go out and measure and regulate and make sure those standards are met. And then consequences need to ensue if those standards aren't met. They also have to do periodic reviews of the cities that are considered harmful. And then they have a real big focus on reducing emissions of sulfur dioxide and nitrogen oxides that can cause or lead to acid rain. They also are responsible for particulate matter air pollution. They are responsible for trying to develop and regulate methods to reduce the sources of, say, the HAPs, the toxic air pollutants, and then also limit chemicals like CFCs that can damage the ozone layer. And so you have this Clean Air Act, you have its amendments, you have its changes, and so you have all of these kind of regulations that need to be set, and then specific agencies that are going to control those regulations. And so after you have kind of this foundation set up, then you have to have an establishment of a series of detailed requirements so that businesses, industries can have something to shoot for. So a goal to go for in terms of meeting these standards and requirements to help improve air quality. So for example, all industries are required to obtain permits to release material in the air. And those permits say they can release air and they can't go over that threshold that they're allowed to release. And so also all new and existing sources of air pollution are subject to air quality standards. So they have to follow those air quality standards. New facilities are going to be subject to more stringent control technology and more stringent permitting requirements than facilities that were built or constructed before them. For the Clean Air Act control requirements, this basically says that the industries have to go in and identify the hazardous air pollutants that they are going to be releasing. And let's say, things like power plants are going to release sulfur dioxide. whenever they burn coal to generate power. Now, if they don't release all of the sulfur dioxide that they were permitted to release, and they actually release less, they can sell their sulfur dioxide release permits to other companies. And so you get a net reduction of sulfur dioxide emissions. And then you also have things like the phase out of CFCs and other chemicals that harm the ozone layer. And another aspect of the Clean Air Act is that in 2007, you had a regulation, or basically a ruling, that greenhouse gases like CO2 should be considered pollutants, and that gave, because they are now considered pollutants, that ruling gives the EPA the authority to regulate greenhouse gases under the Clean Air Act. And so because of that, in 2011, they established new regulations on those greenhouse gases and the release of mercury and other substances that are toxic. Now, we have specific actions that have actually reduced the air pollution that exists globally. The Clean Air Act is kind of a major success story that's helped to reduce atmospheric pollution. And so that just kind of shows that we have a method, we have ways that we can reduce those pollutants. We've just got to regulate and get those implemented. And as we've mentioned, there are several different sources for these air pollutants. One of those primary sources is motor vehicles. They release a lot of the primary pollutants: carbon monoxide, VOCs, nitrogen oxides, ozones. And this has led to very strict, not very strict, but emission standards being set on motor vehicles, and some states like California having specific emission standards that motor vehicles and other machinery kind of has to fall under. You also have particulate matter emissions being regulated. For example, road dust is a big source of larger particulate matter. Construction, industrial activities, mining, farming, all of them add to particulate matter. Fires, regardless of what kind, add particulate matter, especially particulate matter 2.5, and then the burning of other fossil fuels for energy sources, etc. Power plant emissions are one of the primary pollutants associated with, or I should say, the primary pollutants associated with power plants are things like we've already mentioned, that sulfur dioxide, the nitrogen oxide, and then also particulate matter. And so again, we need to just kind of look at ways that we can control these power plant emissions and to really regulate the sulfur dioxide and the nitrogen oxides that come from the power plant emissions. And typically, when you're controlling the release of these pollutants, you're involving processes that are technical, and they're expensive. So a lot of companies, they want to maintain their profit margin, so they really would prefer not to have to spend money on regulating these emissions, right? But we need to do so that we can make sure our environment and the air we breathe is healthy. In terms of looking at air pollution in the developing world, much of the economically developed world has made strides to improve air quality. Lesser developed countries, not so much, because they, again, are just kind of focusing on surviving. They're focusing on getting the resources they need. They don't have the economic foundation to really put into focusing on pollution and emissions, right? In 2011, you have the WHO publishing a study of the impact of outdoor air pollution on world health. Basically, what they found is that about 1.3 million premature deaths were attributed to outdoor air pollution. 800,000 of those were in Asia and the Eastern Mediterranean areas, where you have a lot of those developing economies. And like I mentioned, not only is the developing world focusing kind of on their subsistence, but they also don't really have the money to regulate their industry and transportation sectors. And so the economic development begins with the development of industry. Right? So they're using cheap labor and environmental regulations that aren't strict to manufacture these products cheaply. And like I mentioned, they're eager to have jobs and economic development that they're accepting a risk of having higher pollution. And so the last kind of couple things we're going to mention is indoor air pollution and noise pollution. So indoor air pollution is basically air pollution within your home. Some of these pollutants are things like asbestos, formaldehyde, which is in consumer products, airborne pesticides, chloroform, paradichlorobenzene, and perchloroethylene are some of the more common indoor pollutants. Some big sources are smoking, so secondhand smoke or direct inhalation, using less efficient kind of windows and doors that allow air to exchange, and then the pollutants get trapped inside the house. And so the EPA is conducting research to identify and rank human health risk as a result of exposure to indoor pollutants. And like I mentioned, secondhand smoke is a big one. So exposure to environmental tobacco smoke in places where you're working around or living with people who do smoke. And so there are EPA recommendations to prevent people from experiencing secondhand indoor smoke. So you have kind of places kind of, banning the smoking in and around their grounds, campuses, work areas, etc., so that they try to limit that secondhand smoke. And so companies have policies to protect employees from that secondhand smoke. But today, only 16 states have some kind of statewide ban of smoking in public places. But even if it's not like a state legislation, a lot of the time cities and businesses will have kind of guidelines on where you can smoke and you can't smoke in those buildings to help reduce that secondhand smoke. So sources of indoor pollutants are things like radon that comes from inert radioactive gas. So it just kind of like comes up from the earth. And it can really harm your lungs. It can cause cancer. That radiation can lead to mutations in your cells and can lead to lung cancer. And like I mentioned, that radon usually comes up through the rocks and the soil, goes into the atmosphere, but it can diffuse into your groundwater and it can become trapped inside your home, where it can build up and where it can then cause problems. Here's a map of where radon may be more prevalent in the United States. I think purple is higher and blue is lower. Yellow is moderate, so you can kind of see where those areas are. So if you live in those areas or you have family members that live in those areas, you just might want to make sure they're aware that those sources of radon pollution can exist and that they just need to be knowledgeable about it. The last thing we're going to mention is noise pollution. And so noise is basically an unwanted sound that you have. And so research has actually shown that exposure to noise can cause both physical and mental harm. Loudness is measured by decibels, and the louder it is, it can cause hearing problems. It can cause blood vessels to constrict. It can disturb unborn children. It can cause seizures. And so it can have a lot of direct effects on people who are associated with that noise pollution. There was a Noise Control Act in '72 that was kind of the first attempt to control the public from detrimental noises or noise. And then you have the European countries actually doing a lot to control noise compared to the US. And so European kind of construct quiet machinery and construction equipment, and then they have, you know, strictly enforced noise ordinances to kind of alleviate these sources of noise pollution. And so here's the summary slides. You know, as always, use them as a guide, a general guide to study. Again, they're not all of the things that you need to focus on for studying the content in this chapter. Make sure you kind of look at all of the other ideas and concepts as well. And as always, if you have any questions, if you have any concerns, shoot me an email, talk to me in the discussion section. And with that, we'll see you in the next chapter.